Alright, welcome back. We're on part 4 now of our lecture about pressure, and there's no real way to talk about pressure without getting into talking about the ideal gas law. In fact, you wouldn't even want to talk about pressure without learning about the ideal gas law. Now, this is a physical law that you probably have learned about someplace else in your education, a physics class, a chemistry class, or something like that. They might have used the word, the gas law, or there's a number of different laws, different names for this law, but in meteorology we always call it the ideal gas law. And we don't have a lot of equations that we use in this class, and we're actually going to use an equation this time, but there aren't very many times in this class that we actually work with an equation. That being said, atmospheric sciences is a lot of physics and a lot of math and so on, but we're just sort of tootling around a little bit here with the one equation. And this is an idea, this ideal gas law, is an idea that relates together our ideas of pressure to our ideas about temperature and another concept that we haven't spent too much time on yet, and that's density. We'll talk more about density in just a minute. But the ideal gas law, in the form that meteorologists tend to use, is P equals rho RT. That thing just to the right of the equal sign that kind of looks like a lowercase p, that is the Greek letter rho. And in this equation, P means pressure, and that rho symbol means density, and the T means temperature. Well, then what is that big R in there? That big R there is just a constant. It's the gas constant. And you can look it up in the back of a physics textbook or something like that, but you don't have to. And you know why? Because we're not actually going to plug numbers into this equation. Rather, we're going to just think about, like, what does it mean for pressure if we increase temperature? Or what does it mean for density if we hold the pressure constant but increase temperature, or something like that. By the way, just because we want to make sure that everybody's on the same page here, let's look at that right-hand side of the equation there. Rho RT. That means rho times R times T. Okay, so when they just run them together like that, that means multiplied by. Okay, just in case you didn't remember that from like a high school class or something like that. So P equals rho RT is the ideal gas law as we use it in meteorology. This can be rearranged to something you may have learned again in physics or chemistry. I know when I was in high school chemistry, PV equals nRT, that's how we say chemistry or something like that. It was a little rhyme. PV equals nRT is another way of rearranging this equation. But P equals rho RT is the form we're going to be using. Real quick, let's talk about density. That rho symbol there. Density means like how much stuff there is in a unit volume. Like how much air is in a cubic meter. How much air. We're going to use units of mass. So like how many kilograms of air are there in a cubic meter? That's going to be our unit, our way of describing density. But again, we're not actually going to plug numbers in here. We're just going to think through things like, well, what happens to pressure if temperature goes up? Or what happens to density if pressure goes down? And so on. This idea of P equals rho RT is pretty fundamental to chemistry and physics and atmospheric sciences and lots of other disciplines and so on. And really, if you get back to that idea that we had about pressure being the force of lots of little molecules bouncing against the surface, well, actually, that kind of makes the whole idea of P equals rho RT make a lot of sense. I mean, if pressure is the force of all these little molecules bouncing off the surface like you see in this diagram here, I can think of two ways that we could increase the pressure on that surface. One would be to increase the number of the molecules that are hitting the surface, just have more of them hitting. Or two, increase the speed of the molecules when they hit. Now, have them hit harder. Both of those seems like they would work. Well, increasing the number of molecules that is hitting the surface, that's a way of saying density. How many molecules are there in a cubic meter so that we can, be bouncing them against the surface? And two, increasing the speed at which they hit the surface is all about temperature. Temperature is about the speed of molecules moving around. If you're taking the ATSEVS113 lab or have taken it already, you know that it's not quite that simple, but faster objects the faster the molecules are moving, the higher their temperature is, and so on. So pressure should be related to density, and it should be related to temperature, and hence, hundreds of years ago, we discovered this whole idea of the ideal gas law and how this should work. Now, we could, and I think actually in your textbook there are some problems at the end of the chapter and so on, where they actually do work through plugging in values of pressure in pascals, plugging in values of temperature in Kelvin and plugging in values of density in kilograms per cubic meter and like actually working through problems, but I don't really find that very interesting because I'm fairly confident you know how to use your calculator. That's not really what I expect to do in this class. Rather, what I want you to be able to do is to think about this in terms of how pressure should change or how temperature should change and so on. And we're going to kind of think through two different kinds of problems in this part of the lecture here. One set of problems are going to be ones where we hold the density constant in the problem. We have some sample of air that we're not going to let the density change. In the jargon of teaching, we call that a rigid container problem. And you'll see, like, for example, things like jars are a good example. A sealed jar with air in it has a certain density. The density can't change. There's a certain number of kilograms of air inside that jar, and the jar can't expand or contract, it's rigid, and so the density is constant. So when you look at P equals rho RT, the R is a constant, and now the rho is also a constant. So as you change T, how will pressure change? We'll work on one of those in just a little bit. But the other kind of problem that we're also going to do, the one labeled 2 on this slide here, is the kind of problems where we keep the pressure constant in the problem. Where we say the balloons are an example of this kind of problem. The pressure inside of a balloon is the same as the pressure on the outside of the balloon. If you increase the pressure on the balloon just changes its volume or changes its density or something like that. But the density and the temperature and so on inside of the balloon, the flexible container, can change. Alright, so let's, well, we're going to have to decide if we really think either of those things is all that close to what we are talking about when we talk about balloon problems and air problems in meteorology. But let's do some examples of the ideal gas law with regard to like a rigid container problem, like a jar of air. Okay, so we got a jar, it's sealed up, there's a certain number of kilograms of air in there, the volume of that is a certain size, so the density cannot change. It is a sealed jar. There's a certain mass of air in there taking up a certain space. That is a constant density. Well, then if we have a problem with a sealed jar there, and we look at P equals rho RT, well basically you have P equals some constant times T. So what's going to happen if you increase the temperature? Like if you put that sealed jar of air onto a burner? Well, P equals rho RT, rho and R are constants, so as T gets bigger, it's not that fancy of math to realize that means pressure gets bigger. So pressure has to increase, which of course makes sense. I mean, as the as the jar heats up, the air molecules inside there are moving faster and faster and faster and hitting the sides of the inside of the jar harder and harder. The pressure inside the jar will increase. And in the same way, if you chilled the jar, like by putting it into the refrigerator or putting it into ice or whatever, the pressure would have to decrease inside the jar because it is a rigid container problem. Make sense? Okay, so of course the atmosphere is not exactly made of jars of air, right? We can't exactly say the density doesn't change necessarily. We're going to have to think about what that means, but not right this minute. Another example then would be like a toy balloon type problem. Now, balloons are flexible. It's a flexible container problem. And again, it's not necessarily entirely obvious, but the pressure inside the balloon is the same as the pressure on the outside of the balloon. So like, whatever you do to the balloon, like heat it up, or I don't know exactly how you heat up or cool down a balloon. I don't know, cool it down by putting it in the fridge or something like that. The pressure inside the balloon is not changing. Okay? Don't get too bogged down in thinking, but what about if the balloon rises in the atmosphere, or because it's lower pressure? Okay, we're not worrying about that. We just mean like in the lab. You take the balloon and you put it in the fridge. You somehow warm up the balloon over here, that kind of thing. Well, it's sealed. A balloon is tied off at the bottom. There's a certain mass of air in there, but since its volume can change, the density of the air inside the balloon can change. The balloon can shrink and get more dense, or can stretch and get less dense. So density is not a constant here, but the pressure will be. Alright, so again, thinking about P equals rho RT, now pressure on the left-hand side is a constant, R on the right-hand side is a constant, but rho and T are not. So if we have to make that right-hand side equal to a constant, right, because it can't change, it's got to be equal to that left-hand side, which isn't going to change, then as temperature goes up, density goes down. And as density goes up, as temperature goes down, density goes up. So like if I took my balloon and put it into the refrigerator and cooled it down, the density would increase. The balloon would shrink up and get more dense. If I took the balloon out of the refrigerator, let it warm up, the temperature would increase, the balloon would get less dense, it would expand. Okay. Of course, the real atmosphere isn't exactly made of balloons of air either, right? I mean, the pressure of air can change. Neither of these examples of what we did with the ideal gas law look very much like the real atmosphere, and that's kind of true. In the real atmosphere, temperature and pressure and density can all change at the same time. Oh no. Well, that makes it really hard to think about, because you can't say something as simple as like, it is very hot today in Nebraska, therefore the pressure is low. No, because it might be also something about the density changing. Or the temperature is very hot today in Nebraska, therefore the pressure is high. No, because the density could be changing too. Turns out that's not a very simple, P equals rho RT just looks really simple. But it turns out this is actually an extremely complicated, nonlinear way of relating these three important state variables. These three important ways of describing what the air is like at any given time. Rats. So this is still a powerful tool. It helps us solve all kinds of problems, and sometimes, like, in a particular type of weather system, the air is acting like it's in a sealed jar, like it's in a rigid container. Or in certain kinds of weather systems, the air will be acting like it is in a flexible container, but the actual ideal gas law always is applying. It's actually one of the most fundamental laws of the atmosphere. It's one of the so-called 7 primitive equations. Let me tell you something about the 7 primitive equations. If you have the textbook, if you have the teacher's edition of the textbook makes it very clear that there's sort of a theme through this whole course. This whole course is really oriented around understanding the 7 primitive equations, 7 basic laws that govern how the atmosphere works. One of them we've actually already seen before. It's the first law of thermodynamics. Okay? We didn't call it the first law of thermodynamics, but that's the law that describes how temperature changes due to things like radiation, conduction, convection, all those kinds of stuff. You know, the kind of stuff we did in the first module of the course. Now, it turns out there are 7 such laws, and the one that we are working on right now is the one that's listed as number 2 on this list. It's the ideal gas law. Now, the first law of thermodynamics, if we actually wrote it out as a mathematical law, it takes up like a whole page of paper. It's a very complicated equation in the atmosphere. Ideal gas law was no big deal. It's just P equals rho RT. It's just that it's an incredibly powerful and hard to think about equation sometimes. Most of the rest of these other equations, continuity equation, conservation of mass, Newton's second law, are also very big, bad equations. But that's okay. That's what atmospheric science majors are for. That's what big computers are for. We're not going to learn these equations, but we are going to learn what they mean and so on. Now, in coming lectures in this module, what we're really going to be learning about is how forces create motion, that is to say, wind in the atmosphere. And that actually is laws 4 and 5 here on the list of the 7 primitive equations that are describing how, in this case, wind is set up in motion based on the forces. But over the course of the semester, the teacher's edition actually makes it very clear what we're really learning is the 7 primitive equations. That's actually a very powerful teaching tool. More importantly, it's very fundamental to how we make forecasts of the atmosphere. When you turn on the Weather Channel or whatever and you see a weather forecast, that isn't just sort of the meteorologist licking his finger and holding it up to the wind and seeing what way the wind is blowing or something like that. It's a very advanced computer simulation of the atmosphere, much like I'm kind of illustrating in this diagram here. And what we are doing is applying the 7 primitive equations to each of these little boxes here to figure out how the atmosphere is changing. Now, if you had the 105 class, you actually know a lot about modeling, and we're going to be talking more about modeling in the context of weather predictions and stuff towards the end of the course. But we're just kind of getting the ball rolling on understanding the 7 primitive equations, which is in many ways the most important thing to learn in an atmospheric science course. So I kind of just want to give you a little sense as to where this was all going. Alright, but we're not there yet. Now, before we end this lecture, let's do 2 quick questions. Question 9. Hey, what are the units of density? Oh, I mentioned them a couple times in this part of the lecture. Did you happen to catch? Are the units of density millibars, kilograms, kilograms per cubic meter, or are they Kelvin? Which of those 4 options is correct? Make a choice from those 4 options and get a little feedback before you move on to question 10.